Hello, everybody. Our first talk today will be by Weiran from Fraser University, and the talk will be on kinetic inverse problems. Thank you.
And thank the organizers for inviting me to give a talk here. So what I'm going to talk about today is about kinetic inverse problem. This subject, I would say, is still at the early stage in the kinetic community. So what I'm going to talk about today is that I first of all will explain the background of inverse problems, and then I will maybe give you some examples, 3 examples specifically, to show you how the inverse problems works for kinetic equations, and then raise further questions. First of all, the inverse problems in general, not just for kinetic equations. Let's say we have a PDE. The operator I denoted as T, and it depends on some parameter eta. So I write the forward problem. Forward problem is what we're familiar with as solving PDEs. And the PDE depends on some eta, and then you are given some data. The data could be like initial data or boundary data. And what we call as a forward operator is, again, what we're familiar with, to say you give me the data and don't have what the solution property would be. So that's what we call as a forward operator. So this operator, it maps the given data into some M of F. F would be the solution. M of F usually will be called the measurement. So you do not necessarily get the full information of the solution, but you get some measurement of it. And this is what we call as a forward operator, which depends on the parameter eta in the system. And the inverse problem basically says, now suppose you give me this forward operator, meaning that you give me enough data and enough measurement corresponding to this data, can you actually reconstruct the parameters in the system? So that's the general question that people ask about inverse problems. And the reason we care about these kind of problems is, in many cases, or maybe in most cases actually, the physical parameters in the system would be unknown. There are very few examples that you can actually exactly get the parameters from first principles. So in reality, what people do, like physicists or engineers, what they do is that they would design experiments to actually test or to reconstruct the parameters in the system. Okay, so theoretically, the subject that we care about inverse problems would first of all be the well-posedness of inverse problems. Now, for forward problems, we're very familiar with the concept of well-posedness, and we have similar concept for inverse problems in the sense that, do you have existence, meaning that if you give me the operator, can you reconstruct, does there exist the parameters that gives you the cross-Monte operator, and is the construction unique? So existence uniqueness also one cares about stability, in the sense that if the 2 operators are very close in some sense, well, the parameters reconstructed be close as well. Okay, so here I was using a modulus of continuity. It doesn't have to be a linear function, it could be something else. Right? And the norms for the nanness will be measured in the operator norms, because these are operators, and the parameters will be in certain H norm that depends on your problem. Okay, so this would be the theoretical part. Of course, well, a large part about inverse problems would be the numerical part, which I will briefly talk about at the end. All right, so let me say that for macroscopic equations, inverse problems for those equations has been like extensively studied. One very, very classical example would be the Calderon problem. So they started with studying the electrical conduction in the medium. So in this case, the equation is basically the elliptic equation with a gamma, which is impractical. In the original Calderon problem was the electrical conductivity. So basically what we want is to say that if you are given the forward map, this forward map is the forward operator that I mentioned. So this time the map basically takes the boundary data and maps it into the derivative, the normal direction derivative along the boundary. This is the very standard Dirichlet to Neumann map. And in the physical mapping, this is called the voltage to current map. And so if you are given this operator, then can you actually reconstruct this gamma? And this problem has really been studied a lot, like over, depending on regularity of your gamma, depending on the space that you are on, and so on. And for this problem, what people know is you do have unique reconstruction. However, the stability is quite poor. And in the sense that you can see here is a logarithmic stability. And for mathematicians, this is stability, that's not a problem. But in application, it is a problem because it means that your reconstruction is actually very sensitive to your measurement because the logarithm is just too weak. Okay, and now for kinetic equation, let me say that there are also all kinds of inverse problems for other macroscopic equations, like inverse problems for wave equations to recover wave speed, or inverse problems for Schrodinger equations to recover the potential, and a lot of things. For kinetic equations, however, I would say that these kind of problems has not really caught the attention of our community. And when we started looking into the kinetic inverse problems, the only type of equations that we could find in the literature was the linear transport equation. People have looked at the linear transport equation, which has parameters of sigma and k. So the scattering, the k is a scattering kernel, and sigma is a cross section. And this is an equation that is used in optical tomography that people want to actually do the inverse problems to decide the sigma and k. And this equation has been really extensively studied by the group, of Chole, Stefanov, Ullman, and Wang from the 90s until today. So there are many works in this area. And in this case, the forward operator that we have here, we call it as an albedo operator, in the sense that we have the incoming data of the density function on the boundary, and the measurement, if you have a very accurate measurement, the measurement would be the outgoing data on the boundary. This is what we call as the albedo operator. Inverse problem is to say that given the albedo operator, can you recover the sigma and the k? And put it another way, to be more explicit, if I tell you all kinds of incoming data that I put to the system, and I tell you what comes out of it, can you actually uniquely reconstruct the sigma and the k? And this problem has been shown to be well posed in the sense that you can uniquely reconstruct all these parameters and you have good stability. The stability, for example, could be measured in the L1 space of the operators. So in this sense, kinetic equations, at least for this one, is much better behaved than like the diffusion equations. Okay. But this was basically it that we found for kinetic equations. And I want to spend one slide to talk about the basic ideas of how it was done. And then I want to extract from the procedures the general ideas to say that what has been done for linear transport can actually be applied to many types of kinetic equations. And then I'll show you three different types as examples. Okay. So
I guess of the question. So the right-hand side is that, so which one is the in term, the last term? It seems that it should be reversed.
Oh yes, actually there was a minus sign. Yeah. You can. Yes, there was a minus sign. So it should be if you. Yeah, I should write like minus v dot grad x so that you have sigma, which contains both the total cross section and then the k is the scattering. Actually, in some of these works, the condition was to say that there has to be non-trivial absorption, which means you have really negative sign before the sigma. So sigma contains two parts. If you want to use the language of absorption and scattering, it contains a part that's the integration of k, and it contains a part that is absorption. So there should be minus sign. That was a typo. Thanks for pointing that out. Okay, so let me briefly say that how the group of Stefanov, how they solved this problem. Now, the solution their solution actually heavily relies on how you can more or less explicitly write out the forward operator, the albedo operator. So in this case, what they are able to do is they are able to actually write out the albedo operator, the lambda here, into, if you expand the inverse operator, some operator J, which I will show you the formulas, some operator K naught, J is, actually, let me just show you the formulas. So you can see the operators J and K below. They look fairly complicated, but the meaning of those two operators are quite clear. The J operator basically says, I have this kinetic equation, right? It has two types of behavior. One is scattering, one is basically a straight line movement, a ballistic movement, okay? And this J basically says, if I construct my data well enough, for example, if you just input a delta concentration into the domain, what happens is the scattering is not going to take much effect, and the main behavior is just going to be a ballistic trajectory. So this J basically encodes in condition that you don't have any scattering, and the second term encodes the condition that you have one scattering, and the rest of the term contains the information that you might have many scatterings. Yes.
By scattering, what do you mean?
So scattering basically corresponds to the K. So you think about this equation as a neutron transport equation.
Okay.
The particles go in, it collides with the background, right? So if there is no collision, that's just going to be a straight line propagation. That's what the J is doing. If there is only one collision and then it goes out, there is a, let's say, a bounded domain. It undergoes one collision, goes out. That would correspond to the second term. And then it could go under a lot of collisions. That is all like looped into the bare mass. So basically the idea at the end of the day is if you carefully design your incoming data and you carefully design your measurement, then you can actually separate the three terms. You can either make the non-scattering term the leading order, or you can make the one scattering term the leading order. Depends on which parameter you want to recover. The one that has no scattering will help you to recover the sigma. One has one scattering will help you to recover the K. So that was basically the idea. Although they did write things out in very explicit format using all these operators. But let me say that the main idea, if you look into the procedure, it's not really about the formulas. So I'm going to put a general framework that one can read from their procedures, and we're going to use these general ideas to actually attack much more general kinetic equations to do inverse problems. So first of all, inverse problem is really like the opposite of forward problems in some sense. So for example, for forward problems, people like regularizing operators, right? You start with something singular, you want system to give you regularity so that you can do complex and controls and things. For inverse problems, that's the opposite. You don't want smoothing, because once smoothing enters, you lose information, you cannot reconstruct what you want. So if you have operators that preserve singularity, that's good for doing inverse operators. And that is one important reason why kinetic equations are really well posed for doing inverse problems, because it has a transport operator. Transport preserves singularity. You start with delta function, it stays as a delta function. Okay, so this is one general idea. Second thing is that if you are doing inverse problems, first of all, you have to make sure you have a well-posed forward problem, because you want your operator lambda to be well-defined. That's a forward problem, right? Now, forward problem, if you have nonlinear equations, well-posedness could be a big problem, as we know for many equations, right? But for inverse problems, although we do need well-posedness for forward problems, however, we have the freedom to design our data in the sense that sometimes we don't need the most general well-posedness for the forward problems. To solve inverse problems, we only need the ones for the prepared data. So if you prepare the data in a good way, you would get a well-posedness for the forward problem. So that's another idea, because this is important for the nonlinear problems. Now, and another general idea that we extract from the previous analysis is to say that you're going to design your data and measurement, which basically is about the lamina, in a way such that you have a very clear separation of the linear and regular part. Like the previous one, there was 3 terms, and depending on what you want one of the terms to dominate. And so that's another thing. And once you get the singular term, usually your parameters are recovered from the singular terms. And then for the regular ones, you want to show the rest of terms are regular. This is where you use the usual PDE analysis. So I listed some very classical tools here to say energy method, maximum principle to do the L-infinity, energy method to do LP. And for kinetic equations, you can also do velocity averaging lemma. This is another thing that is quite specific to kinetic equations, because in kinetic equations, besides the transport operator, very often you will have some averaging V operator in the rest of the equations. So think about the, for example, the neutron transport. You have average of F in velocity minus F, right? Or even the Boltzmann operator, you have integral operators in V. So those ones, sometimes you want to use like velocity average lemma to show that those ones are more regular part and to separate them from the singular part. Okay, so these are the general frameworks, and I mentioned this briefly already about the transport operator, but I want to make it very explicit here to say that why transport operator is particularly useful for doing inverse problems. The reason is because if you have just a transport operator with the incoming data over a boundary domain, you can just solve along characteristics, right? And then you can basically get your solution using the incoming data. This particular format of integrating from time 0 to t minus is what we call as the backward exit time. So you start with xv in the domain, you move backward along the trajectory, and you hit the boundary. That's the time that we call as t minus, the backward exit time. Okay. So this kind of integration is basically integration along a straight line. And this is well associated with the so-called X-ray transform. So the X-ray transform is to say that you give me an L1 function in RD. If I just integrate the L1 function along a straight line, if I know the integration for every straight line that I do the integration, then I basically can reconstruct my function U. And so this is why very often in the inverse problems for us, you will often see that we get to X-ray transform of what we want to recover, and that's basically the end of the story. And the reason the X-ray transform comes in is really because of the transform. Okay, so this is another structure I want to point out. And then let me say that the examples I want to talk about today would be 3 examples. I will not get into much analysis. Only for the first one, I'll talk a little bit about analysis. At the end of the day, the analysis is not that hard anyways. It's much easier than forward problems, I would say. And so I will just point out the ideas of how do you separate the lead orders from the rest. So the 3 examples I'm going to talk about. The first one is, this is like the test case, although it does have some applications. This is a test to say our general ideas of separating the singular decomposition would apply to nonlinear equations. So in that case, we would go from the linear transport in the literature to, first of all, a nonlinear equation. And the second one, the third one, are more realistic examples. The second one is to say that I have 2 layers of materials. So in this case, one is the aluminum, the other is the silicon. This is coming from a physics paper to study the thermal conductivity. What they notice is there will be a temperature jump at the interface of the 2 material. And what we want to recover in this case would be transmission and reflection coefficients at the interface. Okay, so that's the second one. And the third one is a Vlasov-Poisson equation. So in this case, this is for the semiconductors where you have so-called doping profiles. And what you want to recover would be the N that I labeled out, which we'll call as doping profile. I'll say a little bit more about the background at the end. And let me say that in the past couple of years, I would say the kinetic inverse problems have been picked up much more than before. So I want to point out a recent work, which is very interesting, by the group of Lai, Weiran, and Yang. So what they did is they successfully recovered the collision operator from the nonlinear equation. Again, by using the idea of capturing the leading order behavior. All these examples, you will see that at the end of the day, you want to do a separation of similarities, the leading order and the rest. Although depending on what problem you are looking at, the way to design the data and measurement can be very, very different. So, okay, and the reason I picked up the first three examples, the first example, as I said, is to test the idea for nonlinear equations. Second example is that it will be a time-dependent equation. See that it works. And then the last one is a more nonlinear equation. The first nonlinearity is relatively weak. It's like a semi-linear equation, but the Vlasov-Poisson equation is indeed more nonlinear. So just to show you that all these things can be done. Okay, of course, the nonlinear one is very. Okay, so let me start with example 1 about the nonlinear transport equations. And I'm just going to directly give you the result that we have, and I'll talk a little bit about how it was done. So I recall the equation above, and at the end of the day, what we're saying is I don't really care so much about what this nonlinearity looks like. This nonlinearity, as long as it satisfies two conditions, that it is only a function that depends on x. So again, think about, for the linear case, think about the neutron transport. You have average of f. That's a function that only depends on x. But here we don't need this capital F to be, for example, it can be a functional f. It doesn't have to be equal. And the condition we need is just to say that as long as you can do a priori estimate to show the capital F in the LP norm is bounded by the LP of incoming for any p larger than 1, then you can uniquely reconstruct absorption coefficient. Here I got the sign correct. Okay, so let me give you a quick example. So this is a so-called nonlinear radiative transfer equation. So in this case, you have not only just the light intensity I here, it is also coupled to the temperature. And clearly you have a nonlinear term sigma A T to the 4th power. Okay, so that would be our capital F. You can see that in this example, the capital F depends on the intensity in a very complicated way. It goes through the second. And what one can do is, if you do a priori energy estimate, you can show that this nonlinear term in the L2 norm is bounded by the L2 norm of the boundary. Again, I'm not showing the details here, just to say that for this example, if you apply the theorem that I just showed you, then it says for this problem, you can uniquely reconstruct the sigma. And now let me just show you about the decomposition. I have been talking about separating the leading order from the rest, the singular decomposition. So what does the decomposition look like? For this general model, the decomposition is actually very simple. The main thing that we use here is a regularization. This F here actually has a regularizing effect in the sense that it could be very singular in X, but it's independent of V, which makes it very smooth in V. So that is the regularization that we will explore here. So for that, we basically decompose our solution into two parts, F1 and F2. F1 will be the leading one, F2 will be the remainder. And let me say that this is an exact decomposition. It's not as simple approximation. And you separate the transport operator as the F1. So think about what's happening here is you input a direct delta phi in both X and B into the system. So the transport will basically keep the singularity. You are basically getting a straight line propagating throughout the boundary. And now this capital F, it smooths out in a V velocity. Once it is smoothed out, then you have a very small support of your solution, then this capital F is going to play very little role. This is how you actually separate the leading order from the rest. Okay, so at the end of the day, what we're going to say is the measurement of the total function F is going to be approximately equal to the measurement just coming from F1, where F1 you can explicitly solve, and it contains the information of sigma A. So that's the basic idea. Okay, so I do have a couple of slides to show you the steps. Let me just go quickly. Usually in mathematical analysis, if you want to be rigorous, you don't just directly use direct delta. So want to approximate it a little bit using the Gaussian and then pass the limit. This is just for mathematical rigor. So the incoming data will basically put in a Gaussian approximating the delta, and the measurement in this case would be that you know roughly the trajectory is like a straight line. So you just measure where you expect the straight line is going to come out. So this is why the measurement function, the kernel here, the psi, is going to be concentrated at the point where you expect your trajectory will go out. That's basically the data and measurement that we design here. If you do such a design, what you are going to have is exactly that the MF is going to be approximately equal to just M of the leading order, where the leading order, because it's explicitly solvable, we'll see that it contains an X-ray of sigma A, so that would solve the problem. And yeah, I do have 2 slides to show you the formulas. I don't know whether you want to look at it or not, but maybe for this one, the leading order, you can see that F1 is solved explicitly, so that measurement of F1 can be, the limit is very explicit, where in the end, you have an exponential function which contains the X-ray transform sigma A. And the X2 part, I just want to briefly point out the regularization here to say that when you locate your measurement around the neighborhood of where you expect the B is coming out, then because this capital F is independent of B, so you can actually make use of a very small support of your measurement to show that Y M of F2 is very small. So this is the basic idea. For the next 2 examples, I will not show you all these details, but just to show you the ideas. So for this one, for the first one, we were using that capital F with smoothing duty. As I said, the way to do the singular decomposition heavily depends on which equation you're looking at. So if the equation changes, the mechanism could change quite a bit. So for the interface problems, let me say that this one, I explained at the beginning that this problem is what the physicists and engineers, and especially material scientists, they care a lot about, because this is about the thermal conductivity in materials. And what they notice is if you have different material next to each other, there will be a thermal drop at the interface. And they want to understand the microscopic origin of what happens at the interface. And there are a lot of methods in the physics and engineering communities where they try to do inverse problems to understand what's happening at the interface, but many of the methods are either restricted to like very special conditions, like very low temperatures, or they get an average information of the interface about the conductance instead of very detailed ones about transmission and reflection coefficients. So I put one picture below to show you that what we want to recover here would be 4 coefficients here. Basically, what happens here is in one layer in the film, in the aluminum in this case, we have one kinetic equation, and in the silicon part, we have another kinetic equations, and they are coupled through the interface. And the interface, we have 4 coefficients, eta 1, eta 2, zeta 1, zeta 2, denoting the transmission and reflection coefficients. And in this paper, in 2017, so the group of Munich, what they did is my understanding from reading this paper is that before their work, the modeling for understanding the interface were mostly by using macroscopic models. So in this paper, they started to use kinetic equations, which would be called the phonon transform equation to actually understand it. But in this paper, what they did is they did the modeling of the equations, and then they did numerical simulation using the using optimization methods, trying to recover those coefficients. And here, what we're going to show is mathematically, you can actually derive formulas for those coefficients using the full norm transform. Okay, so the setting would be the film usually will be very, very thin. So I'm putting x from 0 to 1 for the film. And the silicon part is usually very, very large. So 1 to L. Now, in what they are doing, they actually put out infinity. But here we're just talking. Okay, so mathematical setting, the full norm transport. The full norm transport that one starts with would be the nonlinear. So in this case, your density function depends on Tx and velocity, which is mu. In this case, because of the symmetry, they use the symmetry in their setting. So it's basically a one-dimensional behavior. And it also depends on omega, which is a frequency here. And now the equation reads as the usual transport, but with a group velocity of v sub omega, and the m sub f. This is a VGK type. So this m is not the Gaussian, but it is a Bose-Einstein distribution, which depends on the temperature, where the temperature relies on the density function in a nonlinear way. I put all those formulas here. You don't have to really read into them if you haven't seen it before, but just to say that this m depends on f in a non-open, although it's different from the Bose-Einstein VGK operator. So this is a nonlinear one, but in their paper they linearized around a certain equilibrium temperature. So that's what we're going to do. We're going to use their models. So I skipped all those procedures about how it is linearized. It's just a standard linearization process to say that once you linearize it, at the end of the day, you're going to have a linearized operator here. And for the linearized operator, there is also an equilibrium state, which is given by the, could see here, I wrote it down, but it's just some form of linearization. So this is to say that which equation we're going to use for both sides. Now the full equation for the whole setting would be, we have F for the film side, and we have G for the substrate side, the silicon side. And they use the same linear equations as the first equations, as the equations here. And for F, you have incoming data at the left end. You have interface behavior with eta1 as the reflection and zeta1 as the transmission coefficient. You have G at the interface. It has also reflection and transmission. At the very end, at capital L, we put a diffusive boundary condition here. It doesn't matter what you put on the right hand at capital L. You can put whatever condition you like. It doesn't affect the problem. And because of conservation of energy at the interface, those 4 parameters that we want to recover actually is reduced to 1 because they have to satisfy certain relations. Right, and so at the end of the day, we can say that we just need to recover the eta1 from the forward operator. And now let me say that what is a forward operator? At this time, the forward operator is not going to be that you put in the incoming data and you measure the F at the left end. Usually what they do is you put in the feed and you measure the temperature at the left, which means you are measuring an averaged value of F. So compared with the first example, we're not having so much information about F because the first one says you know everywhere what F is. Here you just know an average sense of F. But what helps us is this time we have the time. So one thing I want to say is steady state equations and time-dependent equations for inverse problems. Usually if you have time, then you do get more information coming from different times. Just think about at each snapshot of time, you get some information. So usually if you are able to do steady state, you should be able to do time for inverse. And in this one, and another thing is, if you do inverse problem for times, usually your measurement can be rougher than if you have steady state equations, like what we have here. We only need an average. And the statement, roughly speaking, is if the group velocities, the relaxation times, and the length of the domain satisfy certain assumptions, which are not very restrictive, so they can actually put this into experimental settings, so that, right? And we are able to uniquely reconstruct the parameters at the interface using this formula. Right? And now let me just show you one schematic to explain what the idea is. The idea is actually very, very simple. Again, as I said, the analysis in all the examples I'm showing you today, none of them is very tricky. They are actually coming from physical intuition. So for this one, basically we're saying that if you have no scattering, so no scattering basically means, I'm going to flip back. No scattering basically means all this, like this double bracket, this time because we have frequency, double bracket means you integrate in frequency and you integrate in velocity. No scattering means you don't have this double bracket in F, you don't have this double bracket in G. Then your F and G basically becomes purely transport equations, right? You can just explicitly solve the whole system. That's not a problem. So if that's the case, what's going to happen? I'm going to input my signal at time t naught at a certain angle, certain frequency. It will propagate, it hits the boundary, part of it will reflect, part of it will continue to transmit into the second layer. Now remember, there is no scattering, so everything is just going along straight lines. The ones that's transmitted into the second, it will get into the right boundary, it diffuses, so it gets absorbed and re-emitted. Once it's re-emitted, it could be re-emitted in any direction. It comes back, it hits the interface, part of it will reflect, part of it will transmit back to the boundary where you do the measurement. You only do the measurement at the very left end. You don't probe inside. And now there is a clear time separation here, which basically says that I know when the first time my signal will be reflected back. Right? Because the signal will be reflected in the first layer. That's the fastest reflection here. I will have to wait for a long time for the information to go through the second layer and be reflected. So in that case, what we're going to do is we're going to input our data very concentrated at a certain angle, certain frequency, and we're going to do our measurement at the expected, at the estimated T1, so that you filter out all the information from the second layer. So at the end of the day, if you design your data and measurement this way, it looks like you only have one layer. You don't have a very complicated coupling of the two layers with interface. But that's sufficient for solving our eta 1, which gets the other parameters as well. So this is what I mean by if you use a little bit of physical intuition, that helps a lot. And now, what about scattering? We do have scattering. Now, this is where we understand that scattering is an average. Average basically means it's a more regular part. Okay? And the part without scattering, all those straight line movements, would be our leading order. That's our singular decomposition. Right? And so at the end of the day, as I said, the data measurement is what I wrote down here exactly as a picture. And the decomposition for both F and G will be that we separate out our scattering. Notice that the scattering part is not F2, it's a full F scattering. So we have to do a priori estimate to say that how smooth this guy is and so on. And then to show that this guy, first of all, F1 is very good. It's just the pure transport, has incoming data, has a reflection. That's it. It is self-closed. We're dropping all the other terms from it. The only thing is you need to make sure that you capture the majority of information in F1. So F2 is going to be small based on two observations. Scattering is smoother. So when you do a very concentrated data, it will be small. And you will have to make sure that you don't get a lot of information from the G, from the second layer. That's our intuition, right? So we'll have to estimate what the G is. For G, you also separate it into two parts. One part is that it drops the scattering, but it picks up every information at the interface. It picks up every information at the right boundary. However, we're using the property that if it only has the pure transport, you'll have to wait for a long time to fill it. That basically means no matter what happens at the interface or right end, you just don't see it if you don't wait long enough. Okay, so this G1, it looks like it's very complicated, but if you measure if you don't wait long enough to do the measurement, G1 is strictly equal to 0. So this is how the two equations are completely decoupled. And G2 again is based on scattering. Scattering is small without other information. That's why F1 is going to be the only dominant term that will give us the recovery. Okay, so that's all I want to say about the interface. So the second example is to play with the time this time. And now for the third example, the Vlasov-Poisson equations, and let's see how this is done. So the physical background of the Vlasov-Poisson equations is 15. Should I? Okay, I'll just wrap up quickly. So for the Vlasov-Poisson equations, this is for semiconductors where you introduce the doping material into semiconductors to change its conductivity. Right? And the modeling is going to be Vlasov-Poisson with the Poisson equation is going to be dependent on the doping profile and this capital N. So what we want to do is we want to recover this capital N. And it's nonlinear because of this rho coupling here. It makes it nonlinear, right? And let me say that in this case, how do we identify the leading order behavior? Again, the main thing is to say if you have the albedo operator incoming to outgoing, you can uniquely recover your doping profile. And I'm going to skip all the details just to say that what we did. The idea is basically to say, what's the difficulty here? Difficulty here is, first of all, we have nonlinear couple. We want to break this nonlinear couple. Second case is actually a bit mathematical. If you think about it, what can happen is in a boundary domain, if you input your, let's say, electrons, it could be trapped inside your domain, depending on what this N is. You could have the case that your electrons may not move out of the domain at all, so that it affects your measurement. So there are two main things that we do to break these two difficulties. To break the nonlinearity, what we're going to do is we're going to input, again, a very concentrated stream of electrons into it, so that although F itself is of order 1, now the nonlinearity is through rho. Rho is an integration of F over V. So this is again an idea of smoothing here. Because of this integration here, having these main observations, because my F is in L infinity, but if my support of F is small enough, then rho is actually very, very small. It basically tells you that the dominant electric field is only generated by the N. So that breaks the nonlinearity. Another thing is that if your N is known to be of order 1, so how do I actually make sure that my trajectory is almost the ballistic trajectory? The way is very simple. You just put in your incoming electric field to have very large velocity. If you think about it, very high velocity gets into the domain, your electric field is of order 1. It doesn't feel it too much before it gets out. So that was basically the intuition here to overcome those two difficulties. And if you do that, at the end of the day, what I want to show you, the reconstruction picture is basically to say that the electric field generated by just the doping profile, its X-ray transform is given by basically the difference of the outgoing velocity and incoming velocity, their difference multiplied by the velocity itself. The velocity is going to be put to be very, very big. In the limit, if you think about it, the outgoing and incoming velocities will be the same. So their difference will be 0. So the limit is not just their difference, but the second order is their difference times the size of the speed itself. That will basically recover this En. Okay. And let me quickly say that the future questions. Now, as you can see that there isn't really a unified way of solving the inverse problems. It really depends on what kind of properties you're looking at. So one thing, theoretically, what we want to continue to investigate is the stability. So far, we did unique reconstruction, existence and uniqueness, but we haven't really done the stability analysis. So that's one thing. And then what are very interesting for applications would be, we want to see how this theory could help numerical implementation. Because so far, what the numerical implementation has been done is through optimization. You input a lot of data, you do a lot of measurements, you try to optimize to see that where you get the smallest mismatch, right? But this is a lot of computation, especially if you're using kinetic equations. So this theory, the unique reconstruction theory, can in some sense tell you what kind of data you should choose, what kind of measurements you should do, so that you can greatly reduce the data that you put into your numerical scheme. So this is one direction we're investigating. Another thing is we're now in talk with physicists and engineers to see what their interest is. For example, for the doping profile thing, this is actually of great interest in the mechanical engineering community. They actually are using Vlasov-Poisson equations, but they might not be recovering the n. One problem they proposed to us would be that the potential might not satisfy just the Poisson equation. And it could be some other kernels. They don't know what the kernel is. So is there a way to actually recover the kernel, meaning that you don't have minus Laplacian phi to the thing? You could have some other operators. So they want to actually recover the PD itself. That's one equation. That's one problem that they are very interested in. Another thing that chemical engineering proposed to us is the oximeter, that you test the oxygen level in the blood, where you shine the light in and read the out, and how you actually use kinetic equations to extract that information. That's also something that's interesting. So yeah, I think let's start here.
Thank you. Questions?
Yes.
I may have missed this, but a few times you wrote that X belongs into omega, which is a subset of R2. Is there a particular reason for two dimensions?
Dimension doesn't matter. Actually, that's another thing that's kind of the opposite to the forward problems. Very often what you see is the higher the dimension is, the simpler the problem is, because you have more rooms to play with your, for example, complex pools and things. There are problems, for example, linear transport, where at the beginning, like the group by Stefanov, you were only able to do the recovery in dimensions larger than just 3. So yeah, dimension doesn't matter.
Yeah. Concerning the Vlasov-Poisson case, there is an argument that P naught is large, so that the characteristics are essentially straight lines.
Yes.
So where does it appear in the theorem?
If you look at this formula, you can see that the P naught is the incoming velocity. So at the end of the day, in the limit, by sending the velocity to or speed to infinity, it's convergent to the X-ray transform.
That means that the solution is means that the solution is concerned localizing velocity or something?
The solution does not necessarily localize. So the high speed serves two purposes. One purpose is for the Wall-Poisson's, in the sense that if you have a very, very large velocity to get into your domain, you can prove that your nonlinear equation is Wall-Poisson, and the trajectory will not be trapped in the domain, just because that it just goes out, right? So that's one purpose for the forward Wall-Poisson's. The second purpose is indeed to say, now I want to recover this En, right? So how do I get the En? With a very large velocity here, this is the formula that, so this V plus is basically your measurement. Because what you do is, this is albedo operator, meaning that you can get all the information of F on the boundary. So V plus is where your trajectory goes out. That's where, and you can, if you have the albedo operator, you have the information on V plus. So you basically take V plus and V minus, which is our P naught. I was using the P naught as V minus, the entering velocity. The trajectory is slightly bent in this way, in this case, because n is order 1, speed is very fast. So it's a slightly bent, let me actually up here. It's a slightly bent trajectory here, where the incoming and outgoing velocities are fairly close to each other. And now the formula that you recover, so in this case, by putting a very, very large velocity, what you get is, first of all, you break this row because it's very concentrated. It doesn't have time to expand to larger supports, right? So then you break the nonlinearity. The second thing is you guarantee that the trajectory is almost like this.
You mentioned something about the regularity of this analysis that you can do at the end after you did the reconstruction. Did you mean that you can do this regularity theory on the parameters that you
the regularity would be, usually it will be like, let me give you one example. Actually, let me just, sorry. For example, for this decomposition, right, what we want to show is that this guy doesn't affect much. The contribution, because we add in the scattering, is going to be very small. So this is where you have, for example, this regularity. We're going to use this in LP and things like that. And in some cases, if it's not so clear that this, because this is F itself, is not F1 or F. Or should be F1 and not F0. It's F itself, which means you will have to do the analysis for the closed system for F and G and show that your F is an LP and so on. Sometimes it's helpful if you do the velocity average because it's the WSP embedded into LQ and things. You just need something that is more regular than something like that.
I have a question. So you mentioned, so these are steady problems, and then you mentioned the transient problem that you could solve
with the time,
right? But sometimes with the time comes regularization, which is exactly what you don't want.
The time.
With the time, your problem might become more regular.
Oh, you mean become irregular?
More regular. So, for example, if there is a PDE, which has two steady states, one with discontinuity and one very regular. And then if you kind of evolve it, you might be then you end up.
That makes sense, yeah. But what I would say is, like in our second example, what you want to emphasize is not the regularizing operation, exactly. Right? You really want to pick your data or measurement in the sense that the transport operator is the dominant one. So even if there is regularization, you try to design your experiment in a way it doesn't play the video.
So how was the data prepared for the Boltzmann operator?
The Boltzmann, so in the work that I quoted here, that's a very different one. In this work, what was done is to, again, eventually it relies on the transport operator. But the design was to say that what they did is to say, I start with my F as the boundary for the boundary data. They introduced two small parameters, epsilon 1 and epsilon 2. So they introduced very, very small data on the boundary. And what they did is to play with F1, the epsilon 1 part and epsilon 2 part to say that I can, roughly speaking, solve my nonlinear Boltzmann equation using a nice combination of these two parts along the trajectories. So that's yeah, it's a very different. I would say for that one, I don't see a lot of physical intuition there, but it's very nice mathematical constructions.
Okay, thank you. More questions? No, then let's thank Weiran again. And we'll see you in half an hour.